Earlier in this unit, we talked about how certain elements are very reactive, like sodium is very reactive because it just has one valence electron. It's just one electron away from having a full valence shell. Atoms bond to achieve a full valence shell, a complete outer shell. Why do they do this? It's because having a full valence shell makes an atom more stable. It's a lower energy position to be in. And just like standing on a ladder, you're more stable when you're at the ground than you are standing up on a ladder. The natural order of things is to be in the lowest energy position possible. So most atoms, for a full valence shell, that means having a full octet, a full set of 8 valence electrons, 2 in the S sublevel and 6 in the P sublevel. You have to remember that the first energy level can only hold 2 electrons, so sometimes having a full valence shell does mean just having 2 electrons if you're near helium, if you're early on the periodic table. So those smallest atoms and ions achieve a full valence shell with just 2, not 8 electrons. Atoms are aiming to form a full valence shell by forming ions. They will gain electrons or they will lose electrons. Or they can form covalent bonds, which is sharing electrons, so that the 2 elements involved in the covalent bond both end up with 8 electrons. Different elements are more likely to form ionic bonds versus covalent bonds, but the general idea here is all kinds of bonding attempt to give atoms a full valence shell. For right now, we're going to focus on ions. An ion is an atom that has a charge. A cation is a positively charged ion. How do we get a positive charge? It happens when we lose electrons. Remember, electrons have a negative charge, so when you lose them, what are you left behind with? You're left with a positive charge. An anion is a negative ion. A negative ion occurs when an atom gains 1 or more electrons. So if you add in this electron with a negative charge, then you increase the negative charge. Here you decrease negative charge, so left with positive. Here you increase your negative charge. An atom is going to form the ion that gives it a full outer shell. A full outer shell, but has the least charge. So if you have a choice between gaining or losing electrons to get a full outer shell, you're going to go with the route that involves the least charge. Charge is calculated by doing protons minus electrons. Protons minus electrons gives you the charge. And you can remember that it's minus electrons because remember, of course, electrons have a negative charge. The charge is always written in the top right corner next to the element symbol. The top right corner contains the charge. It'll have a number as well as a sign. You always have to include the sign, even if it's a positive number. So you always include whether it's positive or negative. But you can omit the number if there's just a single positive or negative charge. For instance, sodium with a charge of +1 can be written sodium with a plus instead of the +1. One thing that I want to just tell you while I'm on this page, how to remember the difference between cations and anions, is that cations are positive. Like a cat has paws, cations are positive. It's a terrible pun, but if it helps you remember it, then it was worth it. Okay, I've given you all the rules for ions. Let's put these rules into practice. So here's an example. aluminum. Aluminum is in group 13 and it has 3 valence electrons. So, how can aluminum achieve a full octet, 8 valence electrons? Well, it could gain 5 electrons, like this. Then aluminum would have a full octet. But aluminum here would have a charge of negative 5. Remember, charge is protons minus electrons, so that's 13 minus 18, and that's negative 5. So we would form this anion, but it has a pretty big charge, negative 5. Is there another way we can get a full octet? Yes, there is. We can also achieve a full octet by losing 3 electrons. So I'm going to X out those 3 electrons because I've lost them in the valence shell. And now I do have a full valence shell of 8 electrons. It's just 1 energy lower than what I normally expect for aluminum. In this case, my charge is 13 minus 10, which is positive 3. So here I've made a cation with a charge of positive 3. Which one of these is more likely to occur? The one that has the less large of a charge. So aluminum with a charge of plus 3 is more likely to occur because it involves moving fewer electrons. The fewer electrons you have to move, the better. So losing 3 electrons is better than gaining 5 electrons. If you do examples throughout the periodic table, you will notice a pattern. Because, of course, the charges that you're likely to form is also related to the valence electrons. So let's just remind ourselves about the valence electrons. We've got 1 valence electron in group 1, 2 valence electrons in group 2, 3 in group 13, 4, 5, 6, 7, 8. So what charges are we likely to have? Everything in group 1 tends to lose 1 electron, so it's left with a charge of positive 1. An oxidation state of positive 1. An oxidation state is just another way of kind of expressing the charge on an ion, at least for the purposes of Chem 1. Group 2, these form ions with a charge of plus 2. They lose those 2 valence electrons. Group 13, those lose these 3 valence electrons to have a charge of plus 3. I'm going to skip group 14 for a second. I'm going to come over here. The noble gases already have a full valence shell, so they do not gain or lose electrons. They're happy as they are. They don't gain or lose anything, so they have an oxidation state of 0. But the halogens, they just have to gain 1 electron to have a full valence shell. So these elements form ions with a charge of negative 1. Similarly, oxygen is just 2 electrons away from having a full valence shell, just has to gain 2 more electrons. So these form ions with a charge of negative 2. The nitrogen family forms ions with a charge of negative 3. So now we kind of meet up in the middle here for carbon. What happens with elements in the carbon family? These usually form ions, or they can form ions of either positive 4 or negative 4. Depends on what they're bonding with. Okay, so you can have carbon with a charge of positive 4 or carbon with a charge of negative 4, depending on what it's bonding with. Let's practice some of these monatomic ions. Gallium is in group 13 on the periodic table. So it's going to have 3 valence electrons. Therefore, its Lewis dot structure is going to look like this. 1, 2, 3. The most common oxidation state, well, like aluminum, it can either gain 5 electrons or lose 3 electrons. It's more likely to lose 3 electrons, so that will be a charge of positive 3. So I can explain that. For full valence shell, can gain 5 or lose 3 electrons. Losing 3 electrons takes less energy. Okay, so there is a pattern on the periodic table, but you should still be able to explain why elements in a particular group end up with ions with a particular charge. Similarly for sulfur, sulfur is in group 16, so it has 6 valence electrons, and we'll draw its Lewis dot structure like this: 1, 2, 3, 4, 5, 6 electrons. And again, for full valence shell, it can gain 2 electrons or lose 6 electrons, and gaining 2 electrons takes less energy. Therefore, the ion formed tends to be sulfur with a charge of -2. Or I guess, since I asked for the oxidation state, you could just write -2. You don't have to draw the ion symbol. So, with these ions, we've calculated protons, neutrons, and electrons before. But now we've started changing the number of electrons in an element. Remember, you can't change the number of protons in an element because changing the protons changes the element. Neutrons don't have a charge, so changing the neutrons doesn't do anything to help you make an ion. So, looking at our periodic table, we can see that bromine has an atomic number of 35, so we know it has 35 protons. If I want to know how many electrons the bromide ion has, this has a charge of -1. Remember, on a previous slide, I told you that the charge equals protons minus electrons. If I want to know how many electrons I have, I can rearrange this equation so that electrons equals the protons minus the charge. So here I'm going to have, 35 protons minus the charge, which is -1. Notice that I'm subtracting a negative. When you subtract a negative, that's the same as adding a positive. And my number of electrons here is 36. Neutrons, this is the same as before. I didn't give you any information about the mass number of this element, so I'm just going to assume that the mass number is related to the atomic mass on the periodic table, which is 79.9. I'm going to round that off to 80. And if the mass number is 80, I'm going to subtract away my 35 protons, and that gives me the number of neutrons, which is 45. So my first row contains 35, 45, and 36. Let's look at arsenic. Arsenic with a charge of -3. Arsenic is element number 33 on the periodic table. And if I want to know the number of electrons, I have to do 33 minus -3. Again, I'm subtracting a negative, which is the same as adding a positive. It has 36 electrons. And again, I'm not given any information about mass number, so I'm going to take my mass off the periodic table, 74.9, and that gives me, I'll just round it up to 75. 75 minus the 33 equals 42, and that's the number of neutrons on the periodic table. Let's look at potassium. Potassium is element number 19 on the periodic table, so that's how many protons it has. And if I want to figure out the number of electrons, that's 19 minus my charge, which is +1 this time. So it's just 19 minus 1. And that gives me an electron count of 18. And this time I'm not going to take the mass from the periodic table because I am given information about the mass number. That's got a mass of 40. And 40 minus my 19 is 21 neutrons. Remember, only protons and neutrons contribute to the mass of an atom. Question D. Strontium is element 38 on the periodic table. And to figure out the number of electrons, 38 minus 2 is 36. And with strontium, I'm not given any information about the mass number, so I'm going to use the one off the periodic table. I'm going to round it off to 88. 88 minus 38 is 50, so 50 neutrons. And our table is complete. I do just want to draw your attention to the fact that each corner next to the element symbol has a different meaning. The charge goes in the top right corner. The mass number goes in the top left corner. This is the mass number. If there were a number down here, it would be the number 19 because the atomic number goes in the bottom left corner. And we haven't started using this bottom right corner yet, but we will. That's where we're going to write the number of atoms when we start writing molecular formulas. I hope this helped.